After studying this module, you shall be able to know what is thermodynamics and kinetics. You will learn the difference between thermodynamics and kinetics of a reaction. You will be able to identify thermodynamic and kinetic controlled reactions. You will evaluate the energy profile diagram of a reaction. During a chemical reaction, the reactants are converted into products. The process can be described by its mechanism. Moreover, the energy changes taking place in each step can be shown using a reaction coordinate diagram. It depicts the transition state threshold which requires certain amount of activation energy. This is because the reactants are not reactive under certain conditions. The reactants must be supplied with enough activation energy to enable the reaction to proceed in the forward direction. The energy is supplied to the reactants by different energy sources like spark, heat, etc. The rate of reaction K and the kinetic energy required for activation of reaction determines how fast any reaction reaches equilibrium. For a reaction A plus B giving D plus E with small d and small e as the stoichiometric coefficients, the K equilibrium can be given by concentration of products divided by the concentration of reactants. So, K equilibrium is equal to product of concentration of D, E each raised to the power stoichiometric coefficient divided by concentration of A and B both raised to their stoichiometric coefficient. So, rate of reaction will be equal to number of collisions per unit time multiplied by fraction with sufficient energy multiplied by fraction with proper orientation. The energy profile diagram for a reaction A plus B giving D plus E is shown here. C is the intermediate formed. In this figure, the delta G naught is equal to free energy of products minus free energy of reactants. Delta G double dagger, the free energy of activation, is equal to free energy of transition state minus free energy of reactants. Any quantity that refers to the transition state is represented by the double dagger superscript. Delta G naught relates to equilibrium constant. The thermodynamic stability is indicated by delta G naught. If delta G naught is negative, the product is thermodynamically stable compared to reactant and the reaction is said to be exergonic reaction. If delta G naught is positive, the product is thermodynamically unstable compared to reactant and the reaction is said to be endergonic reaction. The kinetic stability of a component is indicated by delta G double dagger. If delta G dagger is large, the compound is kinetically stable because it does not undergo that reaction rapidly. If delta G dagger is small, the compound is kinetically unstable, that is, it undergoes the reaction rapidly. For a reaction to take place spontaneously, the free energy of the products must be lower than the free energy of the reactants. That is, delta G must be negative. The Gibbs standard free energy delta G change has an enthalpy component and an entropy component which are related by the equation delta G equal to delta H minus T delta S. The enthalpy term delta H is the heat given off or the heat consumed during the course of a reaction. In a molecule or compound, the atoms are held together by bonds. When new bonds are formed, heat is given off, and when bonds are broken, heat is consumed. Thus, delta H is a measure of the bond making and bond breaking processes that occur as a reactant are converted into products. Entropy, delta S, is defined as the degree of disorder of a system. Exothermic reactions. If the bonds that are formed in a reaction are stronger than the bonds that are broken, more energy will be released as a result of bond formation than will be consumed in the bond breaking process, and delta H will be negative. Therefore, exothermic reaction is a reaction with a negative delta H. In exothermic reaction, the products are more thermodynamically stable than the reactants. The equilibrium constant for the reaction will be large. K is greater than 1 for exothermic reactions. This has no effect on the rate of the reaction. The rate depends on the activation energy EA. Now we will discuss about endothermic reactions. If the bonds that are formed are weaker than those that are broken, delta H will be positive. Therefore, endothermic reaction is a reaction with a positive delta H. In endothermic reactions, the reactants are more thermodynamically stable than the products. The equilibrium constant for the reaction will be small. K will be less than 1 for endothermic reactions because delta H is positive. This has no effect on the rate of the reaction. The rate depends on the activation energy EA. There are certainly two factors which decides the outcome of a reaction. These are thermodynamic factor, the relative stability of the products. Other is kinetic factor, which describes the rate of product formation. Now let's have a view of thermodynamics. Thermodynamics is that branch of chemistry which describes the properties of a system at equilibrium. The more stable a compound, the greater is its concentration at equilibrium. Thus, if the products are more stable, that is, have a lower free energy than the reactants, there will be a higher concentration of products than reactants at equilibrium, and K equilibrium will be greater than 1. On the other hand, if the reactants are more stable than the products, there will be a high concentration of reactants than the products at equilibrium, and K equilibrium will be less than 1. As K equilibrium is equal to ratio of concentration of products divided by reactants, each raised to their stoichiometric coefficient. Therefore, whether reactants or products are favored at equilibrium can be indicated either by equilibrium constant Keq or by change in free energy delta G naught. So, thermodynamics is only concerned with the final state of a system, and the mechanism of transformation does not matter at all. The following comments help to clarify the meaning of this statement. The thermodynamic quantity is the energy difference resulting from the free energy delta G given off during a chemical reaction, that is, the stability of the products relative to the reactants. A thermodynamically controlled reaction involves higher temperatures and long reaction times to ensure that even the slower reactions have a chance to occur, and all the material is converted to the most stable compound. All the substances tend to be in the lowest energy state, so when a substance is at lower energy, it is more stable. Thermodynamic stability has to do with the relative energies of reactants and products, and it is independent of the pathway. One can think of thermodynamics as the energy stored within a reaction, a reactant or a product. With relation to Gibbs free energy delta G equal to delta H minus T delta S, thermodynamics is either the energy released during a reaction, in which case delta G will be negative and the reaction is exothermic and spontaneous, or the energy consumed during a reaction, in which case delta G will be positive and the reaction is endothermic and non-spontaneous. Now let's have an overview of kinetics of a reaction. Kinetics is the study of the experimental measurement of macroscopic properties of a reaction mixture and how the concentration of products and reactants change over time, that is reaction rate. Kinetics describes the rates of a reaction and how fast equilibrium is reached. It gives no information about conditions once the reaction reaches equilibrium. A kinetically controlled reaction involves lower temperature and shorter reaction times, which ensures that only the fastest reaction has the chance to occur. The quantity related to kinetics is the rate constant K. It is associated with the activation energy required for the reaction to move forward, that is the reactivity of the reactants. Knowing whether a given reaction is exergonic or endergonic will not tell you how fast the reaction occurs. Kinetic stability has to do with the pathway between reactants and products. Kinetic stability is largely dependent on the activation energy for the reaction. The activation energy is determined by the chemical potential energy of the reaction intermediates. If the activation energy is high, then at low temperatures the reaction will be slow. It can be made faster by increasing the temperature. If the activation energy is low, then the reaction will be fast even at low temperatures. Such reactions do increase their rates with increasing temperature as well. The smaller the E activation, the faster is the reaction. Thus, anything that destabilizes the reactant or stabilizes the transition state will make the reaction go faster. Some exergonic reactions have small free energies of activation and therefore can take place at room temperature. In contrast, some exergonic reactions have free energies of activation that are so large that the reaction cannot take place without adding energy above that provided by the existing thermal conditions. Endergonic reactions can also have either small free energies of activation or large free energy of activation. Delta S dagger equals to entropy of the transition state minus entropy of the reactants. Delta H dagger equals to enthalpy of the transition state minus enthalpy of the reactants. Delta G dagger equals to delta H dagger minus T delta S dagger. The rate of a chemical reaction is the speed at which the reacting substances are used up or the speed at which the products are formed. The rate of a reaction depends on the following factors. First is the number of collisions taking place between the reacting molecules in a given period of time. Greater the number of collisions, the faster will be the reaction. Second, the fraction of collisions that occur with sufficient energy to overcome the energy barrier of the reacting molecules. Smaller the free energy of activation, more will be the collisions leading to product formation. Third, the fraction of collisions occurring with proper orientation. So, rate of reaction will be equal to number of collisions per unit time multiplied by fraction with sufficient energy multiplied by fraction with proper orientation. Increasing the concentration of the reactants increases the rate of a reaction because it increases the number of collisions that occur in a given period of time. Increasing the temperature at which the reaction is carried out also increases the rate of a reaction because it increases both the frequency of collisions, molecules that are moving faster collide more frequently, and the number of collisions that have sufficient energy to get the reacting molecules over the energy barrier. For a first order reaction A giving B, rate is proportional to the concentration of A. If the rate of a reaction is proportional to the concentration of only one reactant, it is called a first order reaction. The proportionality symbol can be replaced with an equal sign if using a proportionality constant K, which is called rate constant. The rate constant of a first order reaction is called a first order rate constant. So, rate is equal to K into concentration of A for a first order reaction. Now, let us see the second order reaction. For a second order reaction A plus B giving C plus D, a reaction whose rate depends on the concentrations of two reactants is called a second order reaction. For this, rate is equal to K multiplied by concentration of A multiplied by concentration of B. Now, we will have a comparison between thermodynamics and kinetics. So, thermodynamics is all about if and kinetics is all about how. So, thermodynamics is if a process or a reaction can occur or not. Thermodynamics is about if a system is in stable or metastable equilibrium. Thermodynamics is about if sufficient driving force is present to enforce a favorable transformation, whereas kinetics is all about how. That is how fast or slow a process can occur, that is determining the rate. Kinetics is about how transition from non-equilibrium to equilibrium systems or between two equilibrium states occurs. It is about how to overcome the energy barrier to finish the transformation from the starting state to the final state, that is from the reactants to the product state. For a reaction irreversible under mild conditions and reversible under vigorous conditions, at a certain temperature, one product changes to another. At this particular temperature, there is change between a kinetic and a thermodynamic product. Now, let's again have a quick comparison of thermodynamics and kinetics. So, thermodynamics talks about how stable a material or system is in one state, whereas kinetics considers how quickly or slowly a change can occur. Thermodynamics tells that a reaction should go if the products are more stable, have a low free energy than the reactants, that is the reaction has a negative free energy change. Whereas kinetics tells how fast the reaction will go, it doesn't tell anything about the final state. The most stable state of a thermodynamic reaction is that of being in the state of products, because The reaction will happen spontaneously without the need for energy to be added to make the reaction go forward. Whereas in case of kinetics, the more stable state of kinetic reaction are those of the reactants in which an input of energy will be required to move the reaction from a state of stability to that of a reacting and converting itself to products. Thermodynamics is related to stability, however, kinetics is related to reactivity. At high temperature, the reaction is under thermodynamic control, equilibrium or reversible conditions, and the major product is the more stable system. Whereas at low temperature, the reaction is under kinetic control, rate or irreversible conditions, and the major product is that from the fastest reaction. The thermodynamic product is the most stable product. The kinetic product is the product that is formed most rapidly. The thermodynamic product predominates when the reaction is reversible, that is thermodynamically controlled. The kinetic product predominates when the reaction is irreversible or kinetically controlled. Here in this figure, it is shown that the conditions under which a kinetic or a thermodynamic product is preferred. Here R is the reactant and A or B are the products formed under different conditions. This figure shows that if activation energy is less, kinetic product will be more predominant. The case 1 is where B is both the kinetic and the thermodynamic product, and there is a small preference for A under the kinetic control condition. Case 2 is when A is the kinetic product while B is the thermodynamic product, and there is preference for A under kinetic control is shown here, and preference for B under thermodynamic controls are also shown. The other way to determine whether a reaction yields kinetic or thermodynamic product is through temperature. That is, at lower temperature the reaction is irreversible and it gives a kinetic product. Whereas at high temperature it is a reversible reaction and the product is a thermodynamic product. Now let us have an overview of some selected examples of thermodynamically and kinetically controlled reactions. The first such reaction is the addition of HCl to conjugated dienes. The addition of HCl to 1,3-butadiene can give two products. One is the 1,2 and another is the 1,4 addition product. The amount of each will depend upon the reaction conditions. The 1,2 product is called kinetic product and the 1,4 product is the thermodynamic product. At low temperatures -80 to 0 degrees Celsius, the kinetic product is obtained as measured due to low activation energy, while at high temperature 40 to 45 degrees Celsius, the thermodynamic product is measured due to greater stability. The 1,4 addition product is more stable as greater the number of alkyl groups attached to the sp2 carbon, more stable it is, more substituted alkene. But 1,2 addition product is formed faster as the transition state for formation of 1,2 product is more stable. This diagram represents the transition state for 1,2 and 1,4 addition products. The double dagger symbol and 1 and 2 in brackets represent the transition state for 1,2 addition, and double dagger in brackets 1, 4 represents the transition state for 1,4 addition. From this we can see that the 1,2 product is a major product at -80 or at 0 degrees Celsius and it is formed faster, whereas the 1,4 product is more stable and it is formed at higher temperature at 40 degrees Celsius. The transition state for 1,4 addition has positive charge in on less substituted carbon, therefore its activation energy is large and formed slowly. Whereas the transition state for 1,2 addition has positive charge on more substituted carbon and has lesser activation energy, thus formed faster. This can be shown here in case of 1,3-butadiene. When it reacts with HCl, two types of carbocations are formed which are in resonance with each other. In one case the positive charge is at second carbon, and in other case the positive charge is at fourth carbon. Now the positive charge is largely on most substituted carbon, and in that case the 1,2 addition product, that is the kinetic addition product, is formed, which is faster, and the other case is the 1,4 addition product formed slower but more than the kinetic product. It is a di-substituted alkene, and this product is formed at high temperature. In this case the intermediate has a positive charge largely on the least substituted carbon. Another example of kinetic and thermodynamic product formation is addition to a 3-methylene cyclohex-1-ene. When HCl adds to 3-methylene cyclohex-1-ene, the kinetic product is 3-chloro-3-methyl cyclohexene, and thermodynamic product is 3-chloro-1-methyl cyclohexene. The formation of enolates involve both a kinetic and thermodynamic relation. Alkylation of unsymmetrical ketones gives two different products because either of the alpha carbon can be alkylated. As a reaction proceeds by formation of enolate in basic medium, and most ketone give rise to more than one enolate depending upon the reaction conditions. So a thermodynamic enolate can give you two types of alkylated product. For example, in the case of 2-hexanone, if a strong and sterically hindered base like lithium diisopropylamide LDA and aprotic solvent is used, the kinetic enolate is major product. However, with protic solvent or weak base, thermodynamic enolate is predominant as seen. The formation of different types of enolates can be explained as follows in this case. In 2-hexanone, the alpha hydrogen of methyl groups are less sterically hindered than the alpha hydrogen of butyl group. Thus, removal of proton from the methyl hydrogen is faster than removal of proton from butyl. In presence of strong base, enolate will not be converted back to ketone, as the enolate is a weak base to regain proton. With weaker base and protic solvent, protons can be transferred reversibly between isomeric enolates and the base. Under these conditions, the more stable enolate will be measured as they are in equilibrium with each other. The more substituted enolate is more stable. Another example is the methylation of 2-methyl cyclohexanone with one equivalent of methyl iodide. It forms both 2,6-dimethyl cyclohexanone and 2,2-dimethyl cyclohexanone. The relative amounts of the two products depends upon the reaction conditions. The enolate leading to 2,6-dimethyl cyclohexanone is the kinetic enolate because the alpha hydrogen that is removed to make this enolate is more accessible, particularly if a hindered base like LDA is used, and slightly more acidic. So 2,6-dimethyl cyclohexanone is formed faster and is the major product if the reaction is carried out at -78 degrees Celsius. The enolate leading to 2,2-dimethyl cyclohexanone is the thermodynamic enolate because it has the more substituted double bond, making it the more stable enolate. Therefore, 2,2-dimethyl cyclohexanone is the major product. if the reaction is carried out under conditions that cause enolate formation to be reversible, and if a less hindered base like potassium hydride is used. Low temperature favors kinetic enolates as the system cannot equilibrate to form the more stable thermodynamic enolate. At high temperature, the more stable thermodynamic enolate is formed predominantly. The regioselective formation of enolates to give kinetic or thermodynamic product can be differentiated as shown here. Thermodynamic enolate are more substituted, whereas kinetic enolates are less substituted. A thermodynamic enolate is more stable, whereas a kinetic enolate is less stable. Thermodynamic enolates are favored by excess ketone. Kinetic enolates are favored by strong and hindered base. Thermodynamic enolate is formed at high temperature, whereas a kinetic enolate is formed at low temperature. Thermodynamic enolate formation takes long reaction time, and for a kinetic enolate, reaction times are short. Thermodynamic enolate is favored by protic solvent, example alcohols, which have slightly more acidic proton than the enolate and favor formation of enol, allowing tautomerism to the ketone. Whereas the kinetic enolate is favored by aprotic solvents, example THF and diethyl ether, as there is no acidic proton to encourage the reverse reaction. Thermodynamic enolates are favored by weaker bases which provide a relatively strong conjugate acid, whereas kinetic enolates are favored by strong bases, example LDA, which generates a weak conjugate acid. Now let us see another example which involves formation of both kinetic and thermodynamic product. It is the sulfonation of naphthalene. Naphthalene on sulfonation with concentrated sulfuric acid gives 1 naphthalene sulfonic acid and 2 naphthalene sulfonic acid under different conditions. If sulfonation of naphthalene is carried out at 80 degrees Celsius, that is under irreversible condition, the kinetic product, that is a 1 substituted naphthalene, is formed. However, under reversible conditions at 160 degrees Celsius higher temperature, the thermodynamic product, that is the 2 substituted naphthalene, is formed. The kinetic product is easier to form because the carbocation leading to the formation is more stable. The 2 substituted product is more stable and formed at higher temperature because there is a bulky sulfonic group at 2 position is sterically less hindered, whereas in the kinetic product, the 1 substituted product, the sulfonic group is close to the hydrogen at position 8. Next is the addition of HCN to alpha beta unsaturated carbonyl compounds, which are also examples involving both thermodynamic and kinetically controlled products. The alpha beta unsaturated carbonyl system has 2 electrophilic centers, the carbonyl carbon and the terminal carbon of the unsaturated system. The nucleophile may attack to give either 1,2 or 1,4 addition product. When hydrogen cyanide is added to an alpha beta unsaturated carbonyl compound, the cyanohydrin is obtained fast and it is kinetic product, and a direct addition product is obtained, while the beta cyanocarbonyl compound is obtained in a slow reaction and it is thermodynamic product and a conjugate addition occurs. The mechanism of conjugate and direct additions are shown. In case of direct addition, the cyanide nucleophile attacks the carbonyl carbon, whereas in case of conjugate addition, the cyanide nucleophile attacks the beta carbon of the alpha beta unsaturated group. So This diagram represents the energy coordinate diagram of the kinetically controlled and thermodynamically controlled addition products of alpha beta unsaturated compounds. Next example is the isomerization of alkenes. When HCl is added to alkynes, it gets converted to an alkene. The E-alkane is formed faster and is known as the kinetic product. The Z-alkane is more stable and is known as the thermodynamic product. The HCl used for the reaction can be generated using oxaloyl chloride in alumina. The progress of reaction for formation of Z or E-alkane is shown in this diagram, and it can see the percentage of Z-alkane increases with time. The E-alkane is formed through addition of the absorbed HCl on the alumina surface. It gets isomerized to the more stable Z-alkene. The reverse is not possible as the activation energy for conversion of Z back to E-alkene is very high. The mechanism for the isomerization of E into Z is shown here. It involves formation of a carbocation and breaking of the pi bond of an alkene. The single bond undergoes rotation and further elimination leads to formation of Z-alkene. The conversion of acid chloride to an ester in acidic medium proceeds via nucleophilic attack of alcohol on the carbonyl carbon. Kinetics gives an insight into the mechanism of a reaction, and rate depends on the concentration of acid chloride. Thus, it is a unimolecular reaction and rate is equal to K concentration of acid chloride. Lastly, we will see the conversion of ATP to ADP. Adenosine triphosphate ATP is the energy our cells produce and require in order to maintain metabolic pathways, DNA synthesis and repair, and any other cellular function we need in order to survive. ATP has 3 phosphate groups. Molecules desired to become as stable as possible and do so by converting to states of lower energies. Thus, ATP, a high energy molecule, gives off a phosphate group and becomes adenosine diphosphate ADP. For this process, an enzyme removes one phosphate group from ATP and makes it the more stable molecule ADP. The energy of activation for this conversion is provided by this enzyme, proving that ATP is kinetically stable. Now, let us summarize what we have studied so far. Thermodynamics is only concerned with the final state of a system, and the mechanism of transformation does not matter at all. We have studied that kinetics describes the rates of a reaction and how fast equilibrium is reached. It gives no information about conditions once the reaction equilibrates. Thermodynamic stability determines the equilibrium constant K, and kinetic stability determines the rate constant small k. If delta G double dagger, the free energy for activation is large, the compound is kinetically stable. We have also studied that if delta G is negative, the product is thermodynamically stable compared to reactant, and the reaction is said to be exergonic reaction. If delta G naught is positive, the product is thermodynamically unstable compared to reactant, and the reaction is said to be endergonic reaction. During addition of HCl to 1,3-butadiene, the 1,2 addition product is kinetic product and 1,4 addition product is thermodynamic product. Low temperatures favor kinetic enolate, and at high temperature the more stable thermodynamic enolate is formed. We have also studied that sulfonation of naphthalene at 80 degrees Celsius gives kinetic product, which is 1 substituted, but at higher temperature 160 degrees Celsius gives the thermodynamic product, that is the 2 substituted product. When hydrogen cyanide is added to an alpha beta unsaturated carbonyl compound, the cyanohydrin formed after direct addition is a kinetic product, while The beta-cyanocarbonyl compound formed after conjugate addition is a thermodynamic product.